Now let us consider the same RLC circuit where our voltage from t is equal to 0 on the right hand side is equal to 12 volts and our current running through our inductor when t is equal to 0 from the right hand side is equal to 30 milliamps. Given the capacitance is equal to 0.2 microfarads, our inductance is equal to 50 millihenries, and our resistance is now equal to 250 ohms, we want to determine our initial current values in each of our branches, i.e. I sub R, I sub L, and I sub C, as well as their voltage as a function of time. To begin, looking immediately after t is equal to 0, the current running through the inductor is equal to the initial current. That is, I sub L when t is equal to 0 seconds is equal to 30 milliamps. Our current running through our inductor is found via Ohm's law, where our current I sub R when time t is equal to 0 is equal to 12 volts per 250 ohms, or 48 milliamps. Lastly, by applying KCL at our top node, the current running through our capacitor is equal to minus 78 milliamps, i.e. our capacitor is discharging. Now, to determine the behavior of our circuit, we need to determine the roots of our equation. Alpha is equal to 1 per 2 RC, which we find to be 10,000 seconds to the minus 1. Omega naught, which is 1 per the square root of LC, is found to be 10,000 seconds to minus 1. Thus, lambda 1 is equal to lambda 2, which is equal to minus 10,000 seconds to minus 1. We have two repeated roots. Since we have repeated roots, our solution takes the form v of t is equal to a1t plus a2, this quantity e to minus 10,000 t. To determine the constants, we need to apply our initial condition as well as the time rate of change of voltage. At time t is equal to 0, a2 is equal to 12 volts. Now, we know the current running through our capacitor is equal to our capacitance times the time rate of change of voltage across, or the time rate of change of voltage is equal to the current running through our capacitor per our capacitance. That is, dv dt is equal to minus 390,000 volts per second. Differentiating our solution, where we had the form v of t was equal to a1 of t plus a2 times that quantity e to the lambda t, our derivative of v of t with respect to t would be equal to minus 10,000 a1 of t plus a1 minus 10,000 a of 2 e to minus 10,000 t. Or our voltage when time t is equal to 0 means a1 minus 10,000 a2 is equal to minus 390,000. We have two equations and two unknowns. Thus, a1 is equal to minus 270,000 volts and a2 is equal to 12 volts. Thus, the final form of our solution is v of t is equal to minus 270,000 t plus 12 e to minus 10,000 t. Graphically, our voltage starts at 12 volts and approaches minus 6 volts approximately around 0.1 milliseconds, then asymptotically approaches our steady state solution of 0 volts. Since alpha squared was equal to omega squared, this solution is known as critically damped. Now, this solution appears similar to our overdamped behavior. It is noted that critically damped circuits typically go from your maximum voltage and asymptotically approach your steady state voltage without overshooting your steady state value. However, we can have overshoots with critically damped solutions.